So sorry for the last time. It's just weird. I mean, I got a call in middle of a recording. Yeah, whatever. So what was I doing? The first question of insect vector is one, right? You didn't eventually get started, right? Yeah. Anyway, let's start now. 3 point masses are placed on the vertex of any triangle of side 1 meter. If these are the coordinates of the center of mass, then the value of whatever. Right. So this is 1 kg. That's it's zero anyway. Doesn't matter. This is 2 kg. It's at yeah, it's like 3 degree angle with that. So the vector over there, it's like side what? Side 1 meter. This will just be 1 upon 2 comma square root of 3 upon 2, but that ends up 2 because you have a 2 over there. Okay, I don't want that. These interruptions, come on. Okay, it's just gonna be what, like it's just 1 comma square root of 3. That's the weighted r vector, and then for this guy the weighted r vector is just 3. So add them, just get 4 comma square root of 3, and then divide by the total mass, which happens to be 6, right? So what do you get is 4 comma square root of 3 and that upon 6, which is like what? It's just, oh, you just want x upon y anyway, so divide doesn't matter. It's like y upon x is squared 3 upon 4, which happens to be not upon 4 for some reason. They are not doing that. Wait, that's like just, that's 2 over there, isn't it? Just 1 upon, oh shit. No, cosine of, well, that is just 1 upon 260 over there, right? Yeah, exactly. That's sort of 3 upon 2 times of that, which happens to be, right. So y upon x is like sort of 3 upon 4, huh? And that's not there for some reason. I wonder why. Now just 1 over there, exact just 1. Yep, it's gotta be the thing. And SP. Oh, that's not going good. Oh, x and okay, fine. X center of mass upon, so it's like 4 upon sort. Okay, let's see. Sorry. So first it's B. Anyway, not going to write this down because I'm not practicing, right? Okay. Particle of mass 2 kg, 2 kg, 1 kg, 1 kg placed in corners of A, B, C, D of a square of side L as shown in the figure. The position of the center of mass is, okay, find center of mass of these guys. Right? What? Side L. Got it. This doesn't actually matter anyway. This guy, it's 2 comma 0. This guy is like, it's 1 comma 1 with test of 1, which is 1 comma 1. And this is just 0 comma 1 anyway. So 2 comma 0 plus, let's write that down, 2 comma 0 plus 1 comma 1 plus 0 comma 1, and all of that upon full mass, which is what, 4 plus 6. Okay, that's this. So just 6 over there, which is like what, 3 comma 2 upon 6. That's our thing. So what do you want? Center of mass is just 1 upon 2 and 1 upon, oh, that times of L, this completing times of L, of course. Like this is the thing, which is just L upon 2 and L upon 3. So that is a next question. Oh, we don't have to write it down. Yeah. Okay, next, the position vector of three particle of masses, this guy, this guy, this guy, are given. If the position vector of center of mass is this thing, find the value of x, y, and z. They gave us position vectors of masses, fine. And oh, come on, are you serious? Find the value of x, y, and z. Star 3 over there. How many masses do you have? How much of mass do you have? I should ask that. So M3 is 3 kg, like 3 so 3, I'm gonna call it like R vector, right? So R3 vector, I'm gonna call it R vector. Just have 3 R vector plus then for this guy just 2. So plus 2 times of 1.1 is like 2 to 2 basically. And that plus, where that other one go? Oh, it's just 1, right? It's just 1, 4, 1, and that's equal to the total mass is just 6 times of this thing, like 3 times of that, just 9, 3, negative 3. Got it. So what do you get, like 3R vector plus just 3, 6, 3. Oh, you know what? Actually, divide by 3 anyway. Just get what? Like R vector is equal to, oh, plus. Just plus 1, 2, 1. That's equal to this without the 3, which is, where did that go? Just 3, 1, and negative 1. Whatever. So what do you get? Just get R vector is equal to 2, negative 1. Yeah. And then, oh, and by the way, this notation, it's also just a vector, but instead of writing it like round brackets of I hat, k hat, j hat, instead of using all that, I'm just writing this kind of array of numbers. It's the same thing, right? Okay. Oh, they're using it like that. Doesn't matter. It's the same thing. So what do you get? 2, negative 1, 2, which, oh, negative 2, sorry. So A is correct, right? Oh, we don't care. We don't care what is correct because we're just solving. Okay, three particles, mass is something, point whose position vectors are these guys, position vector of the center of mass is. Likewise, position vectors, the mass is, oh, come on, it's just getting boring now. Yeah, whatever. It's like 1, 2, 1, add these up, what do you get? 1, and then it's like, so the x coordinate is how much is 1 plus 4 plus, Oh, what about the y coordinate? It's 1 minus 2. So that cancels anyway. The x coordinate is all that it actually has. Just 1 plus 4 plus 3, which is 8. And 8 upon the mass, which is just 4. So 2, 2i, that's it. So B is the answer. Next question. B's mass is, okay, like meter stick. The center of mass of the system will be as like summation of, yeah, whatever. Oh, these are just 1, 2, 3, and so on, huh? It's like 1 squared plus 2 squared plus 3 squared, keep on going, 100 squared, which, I mean, you know the thing, right? Summation of r squared from 1 to n is just n times of n plus 1 plus 2n times of 2n plus 1 upon 6. So in this case, n is like what? It's just 100. So 100 times 100 plus 1 is like 111. 2n plus 1 is just 201, and that upon 6. So yeah, that's the summation of MIRI, and that upon summation of MI, which is just 1, 2, 3 till 100. It's like 5050. You know the calculation, right? Honestly, don't even write that. It's like 100 times 101 upon 2. That makes sense. This cancels. Just get 3 over there. 201 upon 3 is like what? You need 18, 6, and then you got 21. It's like 67. Yeah, 67. Which, oh, that's not there for some reason. That should have been there though. Huh. Wait, did I do that correctly or not? 2n plus 1. Yeah, 201 over there. 6, it's like about 3. Wait, 18, that's 21 is like 7. So it should have been 67. There's not that. Center of mass of system will be 67, right? What else? Can I mess up somewhere? It just squares. Exactly. So well, this should work out. Huh. This is not making sense. It should really just work out. Wait. No, it has to be that. Just 67. It has to be 67. How could it be anything else? I make us some very bad mistake. It doesn't look like that. It's n times n plus 1 upon n times of 1 plus 1 upon 6, and then n plus 1 upon 2. Exactly. Exactly. Just first 100, right? Yeah. 1 squared, 2 squared, 100 squared. That also works out. Yeah, but it's got to be 67. That's not their fault. It has to be 67, whether you take it or not. Next question. Yeah, I mean, it does happen sometimes that they put up wrong answers, but then whatever. Ignore those. 3-point masses. Okay, center of mass of these. Okay, their center of mass is given. A fourth mass of this guy is placed at. That was the thing, right? Summation of mi. Yes, that's the thing actually. Okay, whatever. Center of mass of the new system is now 0, 0, 0, 10. So as I told you, you can pretend as if the whole system was center of mass for calculating new center of masses. Does that make sense? So this is just like what? You got a center of mass, you have how much is the actual mass of this thing? It's just 3 and 3 is like 6. So 6 times of this is just 12, 12, 12. And then okay, so 12, 12, 12 just has to be negative 3, negative 3, negative 3, right? So this 4-gram guy has to be kept at negative 3, negative 3, negative 3, which is C. We don't have to write that now. Okay, so the following statements are true or false. Center of the system cannot lie outside of the body. It can. It definitely can. Look at this. Look at this arc. Yeah, or like if you really want. Look at this. I mean the thing that we had, the actual like how do I even explain this? There should be a name for this structure, right? This hemisphere in quotations. Yeah, because it's not exactly a hemisphere, it's different or whatever. So this does have center of mass at something that's not a point of the body, right? And it is a 3D solid body, so you can't just say that, oh, but you know, it's a 2D body. Well, no, it is not. So for example, like for something like this, you could say that, but then for a 3D body, no, not possible. Okay, so what do you have? So the following, true or false? First is false. System of 4 kilometer points, the center of mass of the system must lie within or... Oh, this is actually a nice thing. I had to prove this while solving maths final lab. Yeah, I mean like while solving final lab, I had to prove this. Um, really. And yeah, actually this does hold true. It must lie within or on the edge of at least one of the triangles formed by the three vertices. This is a true thing. And this has a proof, like, should I actually even tell you the proof? There's no counter example to this thing that you can think of most likely. So you can say it's just assumed to be true. No, I'm going to prove this actually. So you have 3-point masses first of all, right? Then you can split this plane into these sections. So if it's inside of that, then it's actually inside of that. You don't have to worry. Actually, you have to worry still because your fourth point mass is not there. Right. So if it's inside, it will be inside, right? Most likely it will be. I mean, it's a centroid, of course. It has to be on one of the medians. So it is inside. Cool. And the quantities of equal mass, I guess. Now they're not of equal mass. Yeah, but still you could just do this thing. It must lie inside. Uh, okay, let's actually start off at 2 point masses first of all. Just have 2 point masses, then it's somewhere on this line segment, and then you have the third point mass which will deviate it away from, so like it's just from some point of this segment and now towards this. So now it's like on this line segment if you want. If this was center of mass's position before this third point was introduced, now it will be somewhere over here, right? Which basically means that it will be somewhere inside this center, sorry, inside this triangle. So you don't, yeah, that at least that much is like you can agree on that, right? It's getting, yeah. So that works for 3 point masses, definitely works. What about the fourth mass? So there are multiple ways you can add the fourth mass. You can add it on one of these regions, right, which are opposite to a side, and then the center of mass will be somewhere on this line segment. But then that is either inside this triangle, or if it's not, it will be inside this triangle. So that works out. And no, I could also draw an obtuse triangle. It will still work out that way. Like for each of these sides, sorry, the regions opposite to the sides, you have this region, and that region. You still have the same thing going on. Also, so some point inside this region, some point outside the regions, and the line segment drawing that, right? So, you know, yeah, something like you can form this region, and it has to be inside it because this line segment is contained inside that region, right? Exactly. If it's not in one of these regions, what other region could it be in? That can be in this region, you know? Yeah. But once again, you can do the same thing, I guess. But yes, like this is pretty much the same. Okay, just have this line segment arm. Guess you could do it in a different way though. Center of this is somewhere, right? Okay. Well, what do we do? Let's talk about the median of this guy. So it has to be on the median. Center of mass is on the median already. And now you have two more sections which have similar properties. It has to be on one of these regions, or it could be just on this thing. But that would mean it's actually, yeah, right. It's either this point, it's in this line segment, or it's over here. In all cases, that works out anyway. So and then it could be on this region, right? But then again, you can argue that okay, this is on this line segment somewhere, and then it's like this triangle. Yeah, this triangle contains it, or it is contained in this triangle, original triangle anyway, right? So you can still say the same argument, right? It works. It works in any case. Yeah, I guess that's nice. Yeah, so that was like a nice visual proof, not exactly very rigorous, but then it's enough to satisfy someone who just wants to see if it works or not. So yeah, it actually does work, and this has to be on one of these triangles. Okay, that's awesome. Okay, where were we? Okay, center of mass system cannot lie outside the body. Yeah, well, that's not correct. Center of mass of 4 points. Center of mass of the system must lie within or on the edge of at least one of the triangles formed. Yeah, okay, that we just proved. All the didn't actually prove it, but then it works in most cases. All the particles of a body are so it we are just assuming it's true. All the particles of a body are situated at a distance r from the origin. Wait, what? Other particles of the body are situated. Oh, okay, okay. Distance of the center of mass of the body from the origin is less than or equal to r. Very interesting. So, okay, so they are like always at r distance. That actually, hmm. Yes, and in fact, it's correct. So it's like a weighted average, isn't it? And that means, right. So because they are on, yeah, and the distance r from this origin, what you have is that the x components, they will obviously be like, okay, we want the distance, not exactly that. Distance, huh? Okay, that is quite a complication. What if we just prove that x is less than r, y is less than r, and z is less than r? Could it still be that their squared sum is more than r squared? Probably not, because you have this thing, x squared plus y squared plus z squared. The square root of this thing and upon 3. wait, not 3. Yes, upon 3, the RMS. That is actually bigger than or equal to just x plus y plus z upon 3. And you know that this thing is actually like, wait, okay, that's not good. Uh, oh shit. That was unexpected, isn't it? Okay, so like x is bigger than r, that would actually make sense, but then this is not making sense. The addition of these guys. Ooh, that's not going good. What you just have to prove is like x squared plus y squared plus z squared is actually less than r if x, y, and z are all less than r. That's not exactly correct, is it? No, it's not. Actually, it's not. So, for example, just take the 2D case. So you have this. So yeah, it could be possible that x and y are less than r, which means they are in this square, but they are still outside. So that's not a good argument. Then what other thing could we do? It's getting complicated. We could just build up like by induction or something, or I could just show another visual proof. Uh, so what are they saying? Okay, it's like at r something. This is not going good. Okay. The position cosines, maybe you could use that somehow. Nah, no, that's not going good. And you want a distance from that. Yes, I know this is true because this works like for small cases, and then you can extend that. But then I won't be writing a formal proof for this. Yes, that is actually true. But then how do I prove this true? So if the points are actually like distinct where these are, then it will be that every time you like add a new vector, so it is show the thing. So let's just start off at one vector. So at single point is our origin. Just have a single point, then the center of mass is also that just point, which means that yeah, it's equal to r. Then you have 2 points. Either you could be on that point coinciding with it, which would mean it's like equal to r, or you could just have some other ways like this is r, this thing is r. This is a very well known thing that the sum of these two vectors, well, they can only be as large as the sum of the magnitude of the vector. So you know, exactly just like 2r, but then that by 2, or you just weighted sum or whatever. So but the basically thing is like this is gonna be on this line somewhere, and what that means is yeah, its distance from this actually is less than this using the Pythagoras theorem. You can prove that its distance is actually less than r or equal to r if it's on these 2 points. And then go to the third vector. So not just yet actually. What we'll do is instead of doing this, we'll just take the center of mass of this guy and use that to calculate the other center of mass. So now the center of mass is like somewhere on this line. It's just some vector that is less than r. And then you're taking another point. Now you can see what's happening, right? This distance from this is like less than r, and this distance is actually equal to r, and then you join these two. You get the thing. Yeah, so distance throughout that will never be bigger than r. Exactly. And just keep on going like that. And then eventually you have n number of masses and so on. So yeah, you're gonna get the final center of mass. And that just proves that yes, its distance from origin is less than or equal to r. But so much for so little. That was pretty obvious, don't you think? Okay, center mass of a particle is at the origin. It follows that the total mass of the particles to the right of the origin is the same as total mass of the left of the origin. Not quite. Not quite. Because how much right? Yeah, that matters as well. So, for example, you just have this thing. This is our origin. You have two masses. You know, the usual example, like it's 1, 4. This is mass 4. This is mass 1. Right? Just have a mass of 4, mass of 1. This is at x equal to -1. This is x equal to 4. Yeah, how are the masses equal? They are not. So, this is like, this is right, and this thing is left. Not equal, definitely not. This is false. Okay, so the third one is true, second one is true, this is false, A is false. Okay, cool. Continuous mass distribution, we just did the thing. We just derived a lot of these cases. Center of mass of uniform values. Oh, we don't need all that. Okay, what is this thing? Oh yeah, okay, this thing, like, we just proved this for any triangle, just that it's centroid, right? Exactly. Oh yeah, this thing. Look, we already have a nice formula for this. This is actually for arc, but more generalized. Okay, cool. And if you want the proof of these formulae, well, you can watch the, I don't remember the name of that video, but it's my notes and proof series, or you can just watch the previous video on this center of mass and collision series. So there I give you the proof of the first formula, not this one because it requires complex numbers. But whatever. Okay, and then what? Integral exercise 2. A rod of length L with linear mass density lambda. Oh, okay. This is the thing that I was talking about. Linear mass density varying linearly with distance. Placed along the axis, right? The distance of vector of mass. So, you just use this formula, but let theta approach and also like, oh, it starts off at what point though? 1 and at origin. So our small r is 0 and our theta is approaching 0. Then it just becomes a rod as we just saw and described it earlier in the last video. So yes, it just becomes like what? It just 2/3 r. That's what the distance is. So the distance of the center of mass from the origin is just 2/3 L. So B is correct. Next question: rigid body consists of 3 kg mass connected to 2 kg mass by a massless rod. The 3 kg is located at this thing, 2 kg is at this thing. The position of the rod is what? Length of the rod. Okay, okay, okay. Wait, I didn't understand. I asked this rod, the 3 kg is located at this thing. Hey, this is like the distance between these, right? What's the big deal about it? Yeah, I mean, this was not even about physics at all. It's just usual distance formula. What is this? Am I missing something? No, probably just the distance between them, right? Okay. So like square root of what? 2 squared plus like 3 squared. Oh, that is okay. 4 plus 9 squared of 13. So probably A. I don't know. Or the question is wrong because the rod could be of any length after all, right? Who told you that the ends of the rods are the masses? Nah, they didn't actually tell us, right? So it could be any length, it could be infinite for all we know. Non-uniform rod of length L having mass per unit lambda varies as this thing, where K is a constant and X is the distance at any point of the rod which is found. Distance of the center of mass from the end is. Alright, this is, I mean, it's doable. It's not like integration of, this is K upon L stuff is like constants. We don't actually need that. It's like what? X square and dx. Oh, that times of X once again because, the Ri thing. And upon the integration of just x squared dx, the mass, right? So that K upon L stuff comes out, it cancels, doesn't matter again. And just what, like from 0 to, and K is a constant, right? Yeah, okay. Oops, what happened? That was not supposed to happen. Okay, so just from 0 to L, right? So length L, this is like 0 to L. Whatever, just get x upon 3, and this is upon on the top, just 2 upon 3, so just 2 upon 3 L over there. Right, resistance of the center of mass from that end. Also 2 upon 3L. Oh shit, no. It's 1 upon 4 and it's like, oh, okay, 3 upon 4L, sorry. So it's B. Yeah. Okay, next question. Rod of length L, non-uniformly distributed mass along its length, linear mass density, something. Okay, well, it's a constant. Position in the center of mass is this thing of case. Are you serious? That is just. Okay. Fine, fine, fine. So they gave us the lambda value, whatever. So we should probably go from indication of length L. But where does it start? Wait, what are its endpoints? Do you even know that? Does it start up at the origin? Does it not? Maybe it could be like this. This is how the rod is. Okay, that's not correct. Maybe this is how the rod is, right? This is our origin. It starts up at here until there. Length L. Who knows? It could be like that, right? And then there's not just a linear function like x square upon 2 will be involved, which means that you need, oh god, this is not good. The position of center of mass. What do you mean with respect to what? What is this question just so vaguely written? I know what they're talking about. It's that origin is an end point and this is L and you get a thing. But then that is stupid, right? We have been doing that for ages now. Anyway, so that just a constant doesn't matter. And yet it's got L plus X whatever. That's what we're integrating. It's got LX plus X square or L square plus X squared upon 2. L squared upon 2. Okay, upon, oh shit, this times of X once again. So it should be not just the integration of this, of that was in the denominator L plus L squared upon 2, and in the numerator you just have what? It's the integration of Lx actually, and yeah, like Lx squared upon 2, just L cubed upon 2, and this thing is x squared, just x squared upon 2, just L cubed upon 3, and this should probably also be L squared or whatever. So what do you get? Just 5 upon 6 upon 3 upon 2, right? Which is 5 upon 9. It's like 5 upon 9 L. That's the position. So K is just 5. Next question. Okay, mass is uniformly distributed on the circumference of a ring of radius A and center of mass at collision. At origin. Okay, circumference of a ring. Non-uniform. Oh, what? Non-uniformly distributed. Okay, let be the distance of center of mass of. Oh, it's just the same as that last question that we did. Where did that go? Yeah, the thing about the radii and all that stuff, right? Exactly. It's like you have n mass at r distance from the origin and all that stuff, right? Okay. Then yes, b is less than or equal to a and greater than or equal to 0. So b looks correct. I mean that was discrete, now just continuous. Nothing changed, right? System of continuous objects. So till now we have been dealing with solid objects as a single thing, right? But now you have multiple solid objects. So you just have, yeah. Anyway, right. So I just showed you how that happens, and what is this thing? Interesting number of n objects having this guy. Come on, that we already know. Just yeah, we already know that one. It's just the definition. So what about it? Okay, whatever. Uniform lamina ABCD made up of square ABDE. Sorry, but okay, this is a square and uniform triangle. Find the center mass of the lamina, and the density is the same for both of these guys. We are assuming, I guess so. Fine, center of mass. Just take the center of this guy, the centroid of this guy, and then figure out the mass of these guys, and then weight them, average them. You get the thing done. Easy as that. The height will be 0 anyway. Yeah, the y coordinate is 0. X coordinate means it's a. Oh, that's like square. Oh god, lot is involved over there. This distance from the base, it's okay. Anyway, no big deal. We can actually do that. Find center of mass of the composite. Right. Density of a system. Right. Okay, we can do that as well. Is it a complete solid body? It's like hollow. Uniform density, I think volume and density. That's like a solid object. Whatever. Nice question, but they already did the thing, so what is left to do? Okay, let's do it. 3 rods, same mass, are placed as shown in the figure. Center of mass of the coordinate center of mass of the system is. Okay, what do you have? Wait. So it's like a comma 0, this is 0 comma a, this thing is. Oh, and wait, rods, right? Oh, I thought it's like masses, whatever. Yeah, so the same mass you're saying. So this is like the first guy is just 0 comma a upon 2. Then the next guy, same mass, all of them. That's why it doesn't matter, a upon 2 comma a upon 2. And then the last guy is just a upon 2 comma 0. These are just the midpoints of these masses because we know that's where the center of mass of these rods will be. Okay, and then upon the combined mass, which is scaled up by, okay, this is like proportional to 3, if that makes sense. Okay, this is what, take that a upon 2 out. It is, it's like 1 plus 1 plus 1 is like 2, and then just same stuff, 2 upon 3, 2 upon 3. So a upon 3 times 1 comma 1, right? Yeah, that's the same, which is B. Next question. Next we have a man has constructed a toy as shown. If the density of the material of a solid is 12 times the density of the solid cone, okay, it's a solid cone. Distance center of mass of system from O is, where is O? This is O. Okay, fine. Right, so with respect to O, this guy's center of mass is like what? It's just 4r upon 4, I believe. Yeah, which is r. So it's the distance r from this guy. And the density is what? The density of material of solid sphere is 12. Oh. It's kind of complicated because, okay, what's the volume of this cone? Shit. Okay, it's like pi r squared minus 1 calculates it. That's the radius of this guy then. Yeah, whatever. What's the volume of this thing? It's just 1/3 pi r squared. H is like what? 1/3 pi r squared, which is like 2r squared, and H is just 4r. Okay, that's the volume, and the density of solid sphere is 12 times of that. Okay, whatever. Okay, this times of, I guess we should just really see what we have. This is the sphere, this is the cone. So first of all, their masses, the ratio of their masses. Okay, so that's first of all, you just need the volume. So the volume ratios just have 1/3 pi molar. Yeah. Okay, so that's the volume of our cone. What about our sphere? It's just 4/3 pi r cubed. Just pi r cubed, of course, very expensive. So this is 8/3 pi r cubed. So it's 2:1, right? Our cone is 2 times as more volume. And then the masses though, the sphere has 12 times density. So this is like what, 6:1. That makes sense. Okay. And the R values or the height values, this is like from O, of course. Sphere, it's 4r plus r, which is 5r, and for the cone it's just r, right? Do the thing, just get what's this, 30 plus 1 upon combined is 7, 31 upon 7, right? And that's not there for some reason. Huh. That was just 12. Okay. Wait, I did something wrong. It's like that's 4r over there. That guy's center of mass is definitely just at r distance from this guy, so that has to be the thing. It has to be the thing, yes. 1/3 pi r squared h, that's what I did, and it's like 4/3 pi r cube. Yes, that's like 8 over there because, oh no, r squared should be 4r squared. Okay, that's right. It is 16 upon 3, so it's 4:1. The volumes are in the ratio 4:1. Okay, then it's like 3:1 over there. Ah, that explains it. So what you get like 15 plus 1 upon 4, which is 17 upon 4. That's still not, sorry, 16 upon 4, which is 64. So 4r, A looks correct. Next question. Okay, uniform wire of length L bent into V shape. Distance of the center of mass from vertex A is, yeah, what is this uniform wire of length L? The complete length is L, and it's like, how do we know how much of length this is and how much of length that is? Wait, wait. This is actually making sense because we don't know if AB and AC are the same. But it's J. We'll just assume they are the same, okay? Yeah, then just like usual rods. Yes. So length L, the distance of the center of mass from the vertex A is. Okay, whatever. Just have some mass of this guy like M, this is at L upon 2, then 30 degree over there. Okay, that's like M upon 2. So you have these two vectors with magnitudes M, L upon 2. Or you know what, you're gonna divide by 2M anyway, so actually just L upon 4. Yes, L upon 4. That's L upon 4. And then this angle between them just 60 degrees. So what's the combined length? It's just, yeah. Or you just say that's 30 degrees. Like cosine of 30 degrees squared 3 upon 2, that times of 2. So the square 3 times this guy, right? Exactly. Yeah, that's what this will be. Just square 3 L upon 4. So that's the distance square 3 L upon 4, which is B. Next question. Masses of 2 kg each are placed at the corners AB of rectangular plate ABC as shown in the figure. A mass of 8 kg has to be placed on the plate so that the center of mass of the system should be at point O. Okay, what is this mass of 2 kg at corners AB? This thing is B. Whatever. Okay. Rectangular plate. The plate has mass of what? Mass of 8 kg has to be placed on the plate so that point O, center of plate. The mass should be. And it doesn't matter because the plate has center of mass at this point anyway. Okay. So wait, where is that? 8 kg to place on the plate. Right. So this is actually 2 over there. This is 2 combined is 4. So right, 4 times, okay, think for it. 2 times this guy, 2 times that guy, equal to 8, or negative of this guy actually, equal to 8 of that guy, right? Which means it's just 4. So 1/4 of the addition of these two vectors, but that upon that times of negatives, like negative 4 times the addition of these vectors, right? Exactly. I guess that's right. That has to be right, of course. That's like 0. Yes, yes, that's right. Just 1/4 of, add these up, what do you get? Uh, right, this is at 4 meters, this is actually 2 meters. Oh, the y coordinates cancel anyway, just 2 meters is like 4 meters. So, that is 2, of course, because, oh, we don't actually want just 2 times, okay, there's like just 4, and then you want 1/4 of this is 1. So, instead 1, it's 1 meter from O, right, on OE. A looks correct. Yeah, because like this is 2 meters. So 2 is 4. That's just 4. This is 8 cancels. So A is correct. Next question. Half of the rectangular plate shown in the figure is made up of material density rho 1 and another of rho 2. The length of the plate is L. Find the center of mass. Okay. Okay. This rho 1, rho 2. This is length L. Combines length L. Okay. Rectangular. Oh, you just want the x coordinate anyway, right? Exactly. Yeah, yeah. We can do this. So this is an L upon 2 or this is actually like what? Oh, it's L upon 4, isn't it? Yeah, L upon 4. And this is a 3L upon 4. And it's like a rho 1, rho 2, whatever. Just the x coordinate, of course. So just 1/4 times so 1. I'm gonna do the thing, of course. Rho 1 times L upon 4 plus rho 2 times 3L upon 4 upon rho 1 plus rho 2. That times of, well, nothing. Yeah, that's what this is. Just L upon 4 common, just get rho 1 plus 3 rho 2 upon rho 1 plus rho 2. So that is a B. Yeah, next question. B should be correct. Next question is resulting volume definition. We already did that once, so now it's not a new concept to you, is it? No. Yeah, we can do that. No big deal. Oh, what about this one? Okay, this is actually a very common example. It's a uniform disk now. I thought it's like sphere or something, but whatever. So disk of radius r rectangle circular hole. So the combined, so the first disk, the original disk has it at origin, so it doesn't matter anyway. This disk has 1/4 the mass, right? Versus radius is like, yeah, and its center is just this point. But then the combined mass would be 3, right? Exactly, it's negative over this. Like, it's not over here, right? Is it? It's negative 1/4 or negative 1 upon 3, right? Okay, so just if this mass is 1, then the combined mass of these two guys is like 3. Does that make sense? Because actually it's negative 1, but whatever. Just negative 1 upon 3 times the radius vector of this guy, which is, you know, just, what is this thing? R upon 2 or thing? Yeah, just R upon 6, I think. Yeah, that's what I did. Find these positions. Hey, we did that. We actually did that, isn't it? Yeah, we already got this formula. So, what is this thing? I'm just getting ugly now. So, what is this uniform radius? Okay, what it is. Okay, placed to the right of. Okay, so that combined body. Fine, fine, fine. This is very weird. Yeah, okay, you understand that. Okay, let's start this one now. How many questions do we just have? Okay, just 5 questions. Easy. Uh, Position center of mass of a uniform disk of radius r from which a hole of small r is cut out. See figure below. The center of the hole is a distance this thing from, oh, whatever. Yeah, so just cut out. This guy's mass is proportional to just small r squared. So just, yeah, just negative r squared is our mi. Our mi plus mi is like this guy. And what is this guy's position? Is r upon 2 from the center of the disk. There you go. That should be doing it. So to the left, right? It's to the left. We just want the, what do you want? Didn't actually tell me what they want. Position, right? But you want like the value or the magnitude? I'm gonna give this thing, whatever. Right. Oh, that's not going good. It's like negative r squared r upon. Oh, that works out, but that's not having a negative. Whatever. The magnitude matches, right? That's good enough for us. So B looks correct. Next question. Center of mass of metal circular sheet of diameter 6, which has 2 centimeters square cut out of it. The two sides of the square lie along the diameters of the circle. OM is the bisector of what is this? What is less than triangle? Triangle OAD, right? Oh, angle. Let's like talk about angle. Okay, AOD, right? But that symbol. Fine. It's just angle bisector. This is a square cut out of it. Okay. So what do you want? Center of this. You want to find a center of mass. So that's wrong. Please center towards A. Towards A. Nope. Towards B. What do you mean by towards B? I don't understand this. Okay, yeah, that looks about right. 0.233 centimeters from O towards, because you're gonna have pi and stuff anyway, so that's better, right? Yeah. So towards M, that should be good. Next, because we just have okay, the mass is proportional to what, like pi r squared. So that thing pi r squared minus this area. Yeah. So you will have bad decimal values. So C looks correct. Won't even calculate it, you already know how to calculate this thing. Find position of center of mass from O of a thin homogeneous plate having form of rectangular, what form of rectangle side R and 2R, from which a semicircle of radius smaller is cut out. Wait, what? From which a semicircle? So this is cut out, and then this was initially just a thin homogeneous plate, right? So this was cut out, right? That's a nice question. Let's actually solve this thing. So center would have been over here. It's at R upon 2, but now you're cutting this off. Okay, so positive and negative, you know the thing. And the center of mass of this thing, we actually can calculate like okay, theta approaches what? Just pi upon 2 now. And this thing is 1, and small r is 0, just r over like 2/3. Then divided by pi upon 2, just 4 upon 3 pi. So it's 4 upon 3 pi of this r value, which is actually this distance. That is what? That's r smaller. Nice. Let's calculate this. So what about summation of mi? So first the mass of this rectangle, it's just 2r squared times, okay, that looks good. The radius vector of this guy, so we just take it from the origin. It's x coordinate with the body. You know what? It's gonna say that. Okay, whatever. Just do it the right way. We know the center of mass has to be somewhere over here, right? So probably it's just better if I take the left direction to be positive. Okay, so what is this going to be? It's at distance r upon 2, I believe. So just r cubed. Isn't that right? R cubed. And then you just have 2r squared. Then minus, because subtracting, okay. The mass of this complete thing is pi r squared. Oh, upon 2. And yeah. So this thing times this times the center of mass's position. Right, that's what it is. So the center of mass's position is just 4 upon 3 pi. That's what we have. 4 upon 3 pi r. And well, that answers this guy, right? So just pi upon 2r squared. This cancel, just get 2 over there. And I cancel this. Let's just get 2/3 r cubed. Awesome. I believe this was correct. Yeah, this must be correct, right? This has to be correct. Okay, so this is the thing. Now you might be thinking, what about the areal density factor? Well, it's gonna get cancelled anyway, right? We don't care about that. So I just got r times 1 minus 2/3 upon what is this? 2 minus pi upon 2. That's it. Just 1/3 over there. Just have 4 minus pi upon 2 upon just like 2 upon 3 times of 4 minus pi, and that's r, which is A, I think. Next question. A square hole punched through a circular lamina, whatever. The diagonal of the square being equal to the radius of the circle, capital R. Okay, find the distance of the center of mass. It's a square. Okay, that's nice. It looks more like not so square thing, but whatever. Find the distance of center of mass of the remaining portion from the center of the disk. The usual thing. Okay, calculate this thing. So first of all, what's the mass of this guy? This distance is just capital R. It's gonna be r upon square root of 2, just square root of that, which is so r squared upon 2, right? That's the mass of this guy, I believe. And it's yeah. We do it. Or you could just say negative mass. So negative of area is what we'll actually be dealing with, because areal density is constant. What is this thing once again? R squared upon 2, right? Yeah, R squared upon 2 is the thing. And well, this times off. Honestly, it looks more like a rhombus than a square, but whatever. Just have R squared upon 2. That's our mass. Then our position vector, which is just negative R upon 2. Okay, then for this guy, that's 0 anyway, right? It's R vector is 0. Then just have this thing negative R squared upon 2 and plus the mass of this guy, which is like pi r squared, proportional to that, but whatever, you get the thing. So what do you get? Just get r cube upon 4 upon pi minus 1 upon 2 r squared. So just get this cancel, just r over there. So 1 upon 2 times of 2 pi minus 1. Did I do it correctly? Yes, I think I did. Or you can just say 1 upon 4 pi minus 2 times r. Yeah, so A looks about right. Next question. Find the position of center of mass of the uniform lamina ABCD as shown in the figure. What ABCD? Okay, A, B, then C and D. Oh, these are not parts of it. Okay, D. Yeah, okay, the usual stuff. You know the thing. This is two. It's life. It's actually isosceles, isn't it? Yeah. So it's a centroid of this guy. Okay, that's a weird thing going on. Oof. Okay, it's like an equilateral triangle. Centroid is at what is this is for 2A, right? Okay. So the area of this bigger one is like 4 times of that. Okay, got it. Just 4 and then upon 4 minus 1 most likely. Yeah. The distance of the center of mass from this guy, that must have been. Oh, wow. This is some weird thing going on. The centroid, first of all. That's what it's going to be. Let's do it right away. Just 2/3. Yeah, what's the height? What's the height of this? Uh, that's 2 over there. That's going to be sort of 3 in that case. But you just want in what ratio? The ratio is 1:2, so it's like just 2/3 of square root of 3, just 2 upon square root of 3, right? Exactly. This must have been at 2 upon, or just take that square root of 3 out because who cares? Just take that square root 3 times a out. Just have, yeah. So for that 2, just have this thing. Oh, it's gonna be complicated. No, do it the proper way. Do it the proper way. So what do you have? Uh, this guy's center of mass. It is well, this is like the square root of 3 over there. So 10.2, right? Exactly. Just square 3.2. Should be enough. Because this is just a over there. And then you're removing this for 3.4, I believe. Oh shit, no. We don't want this. We just want the centroid, not this midpoint. Right. So essentially what ratio 2 is to 3? It's 2/3 of square root of 3, right? So like 2 upon square root of 3. Okay, then minus 1 times this guy's center mass, which is actually just right, is square root of 3 upon 2 over there, which is 2/3 of square root of 3 upon 2, which is seriously 1 upon square root of 3, right? Yes, I believe in that. Uh, yes, it's just 2 times of that. That actually makes sense. Ooh. So what do you get? 1 upon square root of 3 common just got 8 minus 1, which is 7 upon 3. So that's the thing. 7 upon 3 square root of 3 times a, which is b. Next question. Shift in position of center of mass. Huh? Oh, okay, right. Okay. So that's pretty obvious. So now we get into kinetics, I think. Yeah, you know that. What is it? Center of mass of common systems. Triangular plate, centroid. Any kind of triangular lamina just has a centroid. Do you even need to classify these? Ah, come on, seriously. That's just so obvious, isn't it? Exactly. It is a centroid of these guys. Like it's just a comma 0 0 comma b, add them a comma b upon 3. Good. Thanks for centroid. Semicircular ring. Ah, come on, we know all this. Creation of positional mass. Whatever. I will explain what I have to explain when we'll see the questions. Oh yeah, okay, center of gravity. Oh, right. So, I mean, the center of gravity is the center of mass if the gravitational field is uniform. What if it's not? If it's not, then it's different. The center of gravity coincides with the mass uniform gravitational field. See, it's the same as I told you. So, for example, like if yeah, I don't know, you have like a very concentrated mass, a very dense mass. So something that's like about to collapse into a black hole or something like that, right? So you have a very dense mass, and then you have some body like this. Then you can't just say that the gravity is like acting on the center of mass, and then yeah, just think about it like no, you can't do that. You can't pretend as if it were on center of mass because that's not valid anymore, right? Because the torque thing won't work the same way. Instead, you actually have to figure out a torque like by hand. And there's also another way of doing it using center of gravity, which we actually don't know a lot about because most of the time it's just the same as center of mass because, yeah, uniform gravity. That works out in most conditions. Okay. Motion of center of mass, velocity of center of mass of system. Okay, yeah, I mean, I will explain all that when actually, you know what? Actually, just explain it right now. Yeah, let's do it. So, as they told you, any change in the point mass positions will actually change the center of mass itself, right? So, using that equation, where that go? Okay, I think it was before that. Anyway, so what the thing is that delta r center of mass, that is the same thing as saying summation of mi delta Ri and that upon summation of Mi, right? Because the way it's defined is just that yeah, that's pretty obvious. Make the denominators common, group some stuff, and you get this thing. But what that means is actually you can divide by delta t and take a limit, which means you can actually write dr vector upon dt, which is like just the velocity. So the v vector of center of mass is summation of mi v vector of each of these point masses or elements or whatever you're considering upon summation of mi. That makes sense. I think it should. Nice. And then you can differentiate once again, just get acceleration, doing the same process. Just take a difference, divide by time, and then say that as limit delta t approaches to zero, just get the instantaneous acceleration. So acceleration center of mass can be given by this thing. Awesome. And there's another important thing that the torque about any certain point can be calculated using center of mass. So okay, I think we're getting into rotational dynamics now. We should not be talking about this thing. But still, just to show that this center of mass thing is actually very powerful, I'm going to show you the derivation. So you just have summation of ri vector cross fi vector, right? Yeah, that's the thing. And then fi vector, instead of writing that, you could just fi vector should probably only consider the external forces. But then even if you consider internal forces, it's not a big deal, right? It's really not a big deal. You can still do it because internal forces cancel their torques anyway. They're on the same line of action, and that's why they cancel. So that means you can actually just think about the actual acceleration of that thing and then write the net force on that particle. Just have mi ai vector. That makes sense. So yeah, this is our torque. So our torque vector is given by this thing. Now you can write this differently because you can actually say that what was I going to yeah, what was I going to say? Sorry. Oh, right. So you can write ri vector as I should have probably used some different symbol for this thing. I'm gonna use a different symbol, all right? No, just use this symbol. Who cares? So we can write ri vectors as r naught vector plus ri dash vector. So what does this represent? Ri dash vector is the vector as seen from the center of mass, and r naught vector is the position vector of the center of mass as seen from the origin. So doing that, you can write this thing as r naught vectors crossed with the summation of mi ai vector, and then plus the sum ri dash vector cross mi ai vector. So now, why did we do this? What's the importance? This thing, you remember, you can actually write this thing as summation of mi times acceleration of center of mass. So it just becomes this thing. the force on center of mass, which means that it's just the torque. Yeah, just the torque of the center of mass. Or, I think we should just say the torque applied on center of mass about the point O. So just torque center of mass. This is getting weird. Call it like tau 1 actually. So this is tau 1, and then this thing is the torque about the center of mass, because these radius vectors are about center of mass. Yeah, exactly. That's what it is. And also, I think we should probably change the acceleration vector such that it actually becomes like acceleration of center of mass plus, yeah, all that stuff, right? Hmm. Uh, yeah, we should probably do that. The thing is that you can actually just split our AI vector as AI dash vector plus AI, sorry, A naught vector. But then this other part that you get, summation of Ri dash vector crossed with Mi and A naught vector, well, this thing just goes to zero, because summation of Mi, what's gonna do? Right, summation of Mi Ri dash vector, that is by definition zero, right? I mean that thing. So it's like saying the position of center of mass as seen from the center of mass, which is just the zero vector. So this thing just goes to zero anyway, which means that you can just write it like that, which is exactly the Ri cross F thing, but as seen by center of mass. So it happens to be the torque. So the torque of any rigid body, or any body in fact, is just the torque of the torque applied on the center of mass about the point O plus the torque about the center of mass, right? This is getting complicated, but yeah, just remember it like that. It's just like tau 1 plus, I don't know, call it like tau naught. That makes sense. So that's why center of mass is really useful a lot of times, because you can do things like these. Yeah. So for example, let's just say you have something in uniform gravitation field, so any kind of uniform field, then the torque about the center of mass will just become zero, right? So that's another important thing that we have. So the tau naught thing, it was what, like summation of summation of Ri vector. You know what? Okay, let's do it the different way. So in this thing, what we did was actually we did the complete, the complete net force thing. So we use net force to actually write it like that. But then it doesn't matter if you use the net force or just the external forces, because the internal forces don't produce any torque at all. So for tau naught, what you could do is just think about the external forces creating torque about the center of mass. So the forces are of this form. It's just MIG vector, and that crossed with RI vector, right? Or RI dash vector. So this summation is like just, Ri, so MRI vector, summation of that thing, that crossed with G vector. And guess what this thing is? Zero. So that means the torque about center of mass to the uniform field is just zero. And yeah, so like it has multiple uses. Yeah, we should probably not be proving all of this right now, because it deserves a video of its own, right? Actually, we already have videos on this thing, but whatever. So just a quick summary, right? Not so quick, but a summary, okay? So yes, that's why we actually use center of mass. That's why we calculate it, because it has so many useful applications. And the next thing that you're learning is application of position of center of mass, okay? Right, of course, of course. You can see it's already torque and all that stuff. So, right, it's hanging like this, and then you want to find what? It's a semicircle. It doesn't look like that though. In equilibrium condition, find the value of theta. Okay, definitely can do this. No big deal. So it's hanging. So you like take any point. Yeah, you take any point and figure out the torque about that point. It should be zero because it's not rotating, or it's like stationary because of that. So what that means is like you can also take this central point, and then this is actually on the radial vector itself, right? Center of mass is just that, but then this is okay, it's slightly different, so you can't just do that. Whatever. So yeah, just figure out the component in the tangential direction, and then do the r center of mass times that thing, and then equate that to the torque because of tension, and tension is just equal to mg. You can do the thing. You can do the thing. It's not a big deal at all. Oh, we already did this, didn't we? Yeah. Okay, and then there's a lot of calculation that you're making us do. Other than this little section where I actually prove the things, there isn't much to do for just calculating center of masses, right? I mean, yeah, why would you want to calculate a center of mass on the test if you already have it calculated? You just need to know all our formulas, that's it. The main thing is just the torque equations. That's where center of mass comes in handy most of times. Also, like the angular momentum equations, you know the thing, they are related. But that is a part of rotation dynamics, not center of mass itself. So, should we just stop here in that case? I don't know. What else do you have? Oh, also this thing. Okay, fine. The rotational kinetic system. Okay. Yeah, whatever. That also is something that I'll explain later, or something that I've already explained in rotational dynamics countless times. So, I think we should just make a compilation of these kind of things so that we don't have to go to different booklets to learn the same thing again and again and again. Yeah, whatever. Okay, so two blocks of mass m1, m2 connected by massless spring, constant force F applied on m1 as shown. Okay, that's a constant force. Initially, the blocks are at rest and spring is relaxed. Acceleration of center of mass will be 0 always as a spring force is an internal force. The acceleration will be constant because, yeah, the net force on this thing is just this F vector because the gravity and normal cancel, doesn't matter in the end. There is no friction. That's nice. So it's just the F vector, and right, that's all it is. And this spring force is actually internal. It doesn't actually matter because this combined is our system. So yeah, the acceleration is constant. Man of mass. How many questions do we actually have? 12 questions. Whatever, we can usually do it. Right. Then next question you have is man of mass m standing on platform of mass capital M kept on a smooth horizontal surface. Okay, if the man moves a distance x with a speed v related to the platform, the distance covered by the platform on the horizontal surface will be related to the platform. Oh, okay, related to the platform, of course. Right. Okay, it's covered by the platform. It's called that distance as y. Who knows? So what do you have is negative y times the platform's mass. That's just the okay. That plus, so the guy itself just moved, right? Just small m times x minus y. Remember, it's with respect to the platform, which is already moved by y towards left. So, or right, or whatever you're calling negative. So that is equal to 0. Easy as that. Y is just mx upon m plus m. Shouldn't be that hard, right? Yeah, that works out. So, okay. So we'll be in, okay, wait a second. They don't have that one. X upon 2. Wait, are you serious? It has to be this thing. We just did the whole. Oh god, what are they doing? Man moves a distance x with speed v related to the platform. Related to the platform, that's important, right? Right. So it's gonna be like x minus y. In reality, of course, it moves by y towards left. So what I'm imagining is like the platform moves by y towards left, and then the guy actually moves towards right by x minus y. So as seen by the platform, he actually moves by x because, yeah, this guy's position changed by negative 1, so this position changed by x minus y. With respect to this guy's position actually changed by x. Yeah, that should be the thing. But I'm being like, this is correct, and that's not there for some reason. X upon, are you stupid? Where did it actually say that small m and capital M are the same, right? I can just disprove this. Come on, just make capital M much, much bigger than small m, and then you'll be asking that, okay, if we move towards right by 5 meters, doesn't the earth technically move as well? So, if you just, okay, this is kind of a stupid argument. Uh, okay. Yeah, whatever. But by common sense, you can say that when the mass is like very very big, uh, just yeah, the center of mass is not changed because there's no horizontal force on the center of mass. There's no friction, nothing. So then, if this guy actually like so complicated, just make the capital M thing so big that right, if it goes by any distance to the right, then this is like almost not moving at all. So with respect to this guy, it's also just that distance, right? So then it's zero over there. So where does that come into your considerations? X upon 2? No, nothing like that. Oh, okay, they have conditions as well. Okay, whatever. X of this same direction in which the mass, okay, man has moved with the mass. Opposite direction, of course. Okay, it will be either B or D. Okay, man of mass equals mass of platform. Then it's just X upon 2. So it's X upon 2 in the opposite direction in which man has moved. Okay, if mass of man equals mass of platform. So yeah, B, did I just say man of mass? Sorry, it should be mass of man. Okay, so that's right. Next. I really thought they actually were going to just say X and X upon 2 and not have the general thing. Two particles of mass m, mass 1 kg, 2 kg initially are 10 meter apart. T equal to 0, they start moving towards each other with uniform speeds 2 and 1 respectively. 1 kg, 2 kg towards each other, whatever. Distance from the center of mass at t equal to 1 seconds is, wait, what are the speeds? 2 and 1. So the center of mass speed is what? Wait, this first guy's like moving at 2, this is 1. Oh, it's 0. Huh. Yeah. The total momentum is just 0, so center of speed is just 0. Which means center of mass is not actually displaced at all, it's 0. So, okay. The original position center of mass from 1 kg masses. So the original position is 5 meters over here, and now, wait, original position, right? Wait, oh, it's 2 kg, sorry. So what do you just have from 1, it should be actually 2/3 over there. Yes, so just 20 upon 3 meters. So A is correct. Velocity center of mass is, it's 0 from the beginning, as long as the particle continue to move with same speeds in the direction, given direction, after t equal to 0. Exactly, B should be the thing. And what else do we have? One particle is released from the same height above the ground under gravity, and the other part under is projected up with the same speed from the ground simultaneously at equal to 0. Released from the same some height above the ground under gravity. Okay, other is projected up with the same speed from the ground simultaneously. The speed of center of mass t equal to 0 is upwards, acceleration at equal to 0 is downwards. No, the acceleration, oh, at equal to 0 only. Huh. Well, yeah, it is just downward. The speed of center of mass is upwards. So A is definitely correct. The speed of center of mass as long as 2 are in air will be upwards, and acceleration of center of mass is always 0. Look, the acceleration is not 0, it's just negative g downwards. The speed of center of mass is initially upwards for some time, then becomes 0. Okay. I guess, yeah, because it's initially positive, then it has to become negative because g is negative, right? So t equal to infinity it becomes negative, right? Acceleration center of mass is always downwards equal to 0. So C is the most correct option. Yeah. And also A, whatever. The acceleration center of mass is always 0. That's just stupid. A wedge is kept at horizontal ground. Its mass is, what is this? MA? Oh, M. Then period A block. Okay, that's weird. Okay, so its mass is M. It's a wedge. Block of mass M released from rest from the top of the wedge. All surfaces are smooth. Okay, velocity of center of mass of the two body system does not change in horizontal as well as vertical. That's wrong. In vertical, it does change, right? It does change in the vertical direction because the smaller mass, small m guy, it can move in vertical direction, although the capital M guy cannot. So capital M has zero velocity in vertical direction, but small m has some velocity. So it does change from 0 to something. So it does change. Velocity of center of mass of this two body system is never 0 in the horizontal direction. Um, it is 0 actually throughout, isn't it? Yeah, it's 0 throughout because initially they were at rest, so the horizontal velocity was 0 anyway. And then there's no force in the horizontal direction, so it doesn't change. Velocity of center of mass of this two body system is always zero in the horizontal direction. So C looks correct. Okay, so C is the only correct one. I really thought they were actually going to give a whole question about this, like figure out in T equal to what, how much does this move and what not. Okay, body falling vertically under gravity bursts into two pieces of different masses in midair. The heavier one moved towards the right, lighter one towards the left. Wait, so it's moving vertically, isn't it? Okay, falling vertically, fine. Right, okay, the center of mass and different masses. Okay, all right. Center of mass of the two particle system shifts towards right, and is the heavier one has moved towards right. Uh, no, their speeds are different as well. That's not a correct argument. It is zero. The center of mass of the two particles neither shifts towards right or left, but continue to move vertically down. So B is correct. The ratio of masses of the two particles will. So it's like you have. I don't know. It's a valid example or not. You have a box containing something that's decomposing into gaseous molecules, and then okay, that's a very complicated example. Let's not go into that stuff. Okay, the ratio of masses of two particles will decide whether. No, no, no. It is zero. The velocity center of mass will suddenly become zero. Huh? What? No. Okay. Next, what you have? Three particles mass something, something, something initially moving along positive direction of three coordinates. Okay. 20 centimeter per second. Due to their mutual interaction, the first particle comes to rest. Second acquires the velocity of this thing. Oh, use consideration of momentum. Come on, is this like what is it? Just too simple, isn't it? Okay, their masses are given. What ratio? Just 2 is to 3 is to 4, right? Center of mass. Well, the velocity center of mass was just you know like 20 over there, and you just have uh respectively. I'm just gonna say it's like in the x coordinate, y coordinate, z coordinate. Respectively, it's just a thing upon 9. That explains it. Just yeah. So upon 9, that's not there. So initially this thing, yes, actually that's right, and it's also finally that thing. So A is right. The velocity center of mass is zero. As the, okay, that's wrong. That velocity never changes because there is no external force. It seems. The velocity of third particle after first comes to rest is always zero. Huh? Third particle after the first comes to rest. So first at rest is always zero. What do you mean by always zero? Isn't this like a specific case? Oh, okay. It doesn't matter what the velocity of second one is. No, that's just wrong. Not always true. Definitely not always true. And what do you have over there? Okay, second advice of velocity of this guy. So it's like 10 times of 10 20. Okay, fine. So what do you have? This thing is equal to 30, right? Because second one. And that times, oh, it distance of mass. So momentum conservation, right? Yeah. Yes. And you just have what 1 comma 2 and plus this guy's mass. Where'd that go? 2 to do that, right? And you just have v vector, some vector that has it. So what do you get? Just 2v vector is equal to well, that 10 divided by 10. So just say v vector upon 10 upon 10 equal to u vector. Whatever, just write as 2 vector upon 10, who cares? Or as v vector upon 5, that also works. So that thing is just equal to you got 4, 6, 8 minus 3, 6, 0, I believe, because that was no k hat. Oh, it has k hat, it doesn't have a j hat. Okay, just 1, 0, 2 in that case. So then just negative 3 of this guy, which is negative 3, 0, then you got 6. Nice. Which is 1, 6, and 2. It's v vector upon 5. So v vector is actually what? 5 times of this guy, just 5, 30, and 10. And that's definitely not this thing. 2.5 or something. Well, no, that's just not correct. These were just integers, right? Momentum conservation and all that stuff. Exactly. Yes, I think that was the thing. Huh? 20, it's like, okay, whatever. That actually works out. First guy comes to rest, second has velocity of this guy, second has 30. Oh shit. Oh, it's not 2, it's actually 4 over there. Okay, sorry for that. Oh, yeah. Well, it should be 2 vector upon 5, right? Okay, so just have 2 vector. C vector is actually just 2.5, 15, and 5, which, yes, so actually C is also correct. So A is correct, C is correct. Yeah, whatever, next question. Next is a boy of mass something standing over a platform of mass something placed over a smooth horizontal surface. He throws a stone of mass something with velocity of something. Okay, boy throws a throne. Sorry, throws a stone. What am I speaking today? This guy is 60 kg. The stone is what? This stone is 1 kg. Velocity 10 at 45 angles it is. Basically like 5 square root of 2 in that direction, 5 square of that direction. This is our momentum, right? Okay. Huh. Smooth, oh god. Smooth horizontal surface. That's a weird thing. Okay, the momentum of boy plus platform plus stone system after the boy throws the stone changes in the x. Okay, it doesn't. Yes, I think in y direction it does change because there's a impulsive normal force. Because I mean, usually if that was not there, this guy would actually move in this direction, right? But it's not. It's not moving. So that means there must be an impulsive normal force. Okay. The displacement of this what particle plus boy on the horizontal surface when the stone lands on ground is 10. So throughout the motion there is no x component force. So it's actually like no, it's not displacing at all. The system is not displacing in the x direction. Okay. Horizontal surface when the stone lands on the ground uh, is 10 seconds like 0. Yes, okay, I wait. You can't just say the displacement is 0, but uh, I mean, fine. You could say that the y coordinate didn't change throughout the whole journey of the center of mass, so it's okay to say that. And the x coordinate also didn't change at all. So this was in fact 0 for the center of mass, wasn't it? Right, so D is correct. So yeah, D is the correct thing. It doesn't matter what these values were because theoretical questions anyway. Two blocks of mass something something placed frictionless floor connected by spring. External kick gives velocity of something to the heavier block. Seriously, we didn't. It doesn't even matter what the spring is doing, isn't it? Yeah, doesn't even matter, right? To the heavier block, so to the 5 kg block, which is 70 momentum, the velocity by okay, just 10 meter per second. That's a no-brainer. Next question: two spheres of mass something initially at rest. Sorry, initially at rest at distance r apart. Okay, due to mutual force of attraction, they approach each other. What do you mean by distance? It's like a distance between center of mass or what? Seriously though, it should tell us when they are separation r upon 2. Okay, the acceleration of the center of mass of spheres would be force of attraction. They approach each other. Something else. It's zero anyway. It's the internal force that's doing the thing, right? So it doesn't actually matter. Center of mass does not change anyway. So it's zero. This is yeah, just like theoretical questions, they're very basic for some reason. When the person A and B exchange positions, then this guy's A, this guy's B. They exchange positions. What do you mean by exchange positions? Like, oh, okay, okay, their masses are different, and then oh, so they're moving, aren't they? They're moving, and oh, they're actually walking on the plank. Fine. This is moved by the center of mass of system. They gave us the masses. Oh, it's filling the blanks or something? Okay, cool. So they changed the position. This M1 guy changed and like, what's this distance? Just 2 meters, right? Yeah, they actually gave us 5, 7, 8. Huh. The 10 kg stuff, common, so it doesn't matter. 5, 7, 8. So M1 is like 5. Okay, so the change in displacement of these M1 plus M2 system, what's that? It's just 5 times this guy just changed by 2 meters. And then plus M2 is just 7. This guy changed by negative 2 meters. And then this guy, which is just 8. And then how much did it change? We don't know. That is equal to 0. Exactly. So what do you guys just get like plus yeah, just negative 4 goes from there. 2x equal to 1, x equal to 1 upon 2, changes to 1 upon 2 meter, which, yeah. So distance moved by the center of mass of the system. That's still 0. The Planck moved 1 upon a distance. Oh, okay, Planck moved towards right, I believe. Because it was positive, right? Exactly, so it's 14 and that's, and negative 4 can, that, okay, yeah, 1 upon 2 towards right. Distance moved by A with respect to ground is, oh shit. So when it said that it changed positions, they actually mean with respect to Planck. Shit. But that was unexpected. So just have with respect to Planck, this is happening, and okay. We'll just do it the other way. Who cares? Just have this thing 5 times of 2 plus x, because with respect to Planck, right? So 2 plus x. It's very weird. Very weird. But fine, just negative 4 over there. Then you got 5x and plus 7x, which is, yeah, you got 12, which is 20. 20x equals 0. So x would just be 1 upon 5. That's not going good, but whatever. Huh. Fine. Can't be a big deal, right? Yeah, I guess it's not a big deal. Okay, so in that case, your plank actually moved by 1 upon 5 meters, like what? 20 centimeters. So 20 centimeters towards right was positive. Distance moved by. So actually, yeah, the position change with respect to Planck, it seems. And the distance would have moved by A with respect to ground. So A just, yeah, 2 plus x over there, which, you know, 220 centimeters. Nice. So for B with respect to ground. So you got minus 2 and then that plus x. So negative 200 plus 20 is like negative 180 centimeters. So 180 centimeters towards left. That makes sense. Okay. Next you have state the following are true or false. Only external forces can accelerate the center of mass of the system. Yes. Momentum of a system with respect to center of mass is 0. Yes, actually that's right. That's right. Because yes, that is right. Okay. Because the displacement vectors, when you add them, it becomes 0. So like changing those are also 0. Okay. With respect to center of mass, that is, yeah. Okay. Internal forces cannot change the kinetic energy system with respect to center of mass. They can. They can change with respect to center of mass. I should actually give an example, shouldn't I? Okay. Well, let's talk about this one. This is actually a favorite example of mine. So you have a guy who is on a platform. Okay, this platform is of course on an axle, and this axle is like perfectly smooth. We are assuming that this whole thing is rotating by omega. Okay, and this guy actually, this has like, he has very big arms. I don't know. He closes in his arms, thus decreasing his own inertia, which means, okay, this guy's inertia just changed. So our omega will increase, but that means like our L omega, half of that, that is the rotation energy that actually increases. So where does this extra energy come from? Ask yourself, where does this come from? Well, it comes from the guy himself. He actually pulls his arms inside. That is, he actually does work on his own arms. That makes sense because, yeah, he actually has to put up a force, a tension in his arms to actually, yeah, allow them to circle in that fashion. And because our f dot r vector stuff is now not 0 anymore, so the summation of that thing for all kind of internal forces, that's not 0. So there is still work done, but just not by the external forces. It's by the internal forces of this system itself, right? Yeah. So no, that's just wrong. Internal forces can change the kinetic energy of the system with respect to center of mass, right? This is just plain wrong. And notice that there's nothing about, gravity or anything like that. It could be in space for all we know. And the thing is like this is perfectly smooth, this axle, because I want this to be, because we don't want any losses to friction. So yeah, if somebody actually did this experiment in real life without air resistance, without friction, yeah, that's actually a very hard situation. Anyway, if somebody actually did that, they would actually see, and increase our angular velocity, but then you have to ask yourself, where does the energy come from? Who is expending energy? We are expending energy because we pulled in our arms, right? We actually have to force them in. They don't go in, actually they try to go out, centrifugal force. This is getting too complicated now because this is actually not a good example at this level, but whatever. Eventually you will understand that internal forces do change the kinetic energy in some cases, like this one. I wish there was a simpler example that I could tell, but this is the best one that I know. Linear momentum. Oh, we already know about this. So, just a summation of momentum of all of the particles. That's the momentum of the system. No big deal. Okay. Yeah, we know that. Okay. Angular. Wait, no, okay, kinetic energy. So it's P square upon 2m or this guy. So the kinetic energy of a particle that's given by P square upon 2m or half mv square. The kinetic energy of a body is kind of more complicated because a rigid body could be rotating as well. It's not just translation, because if you just translate it, then cool, P square upon 2m half mv squared works out. Every particle has the same velocity. What if that's not the case? What if the particles are having different velocities? Then that's a complicated thing, isn't it? Right? For example, the spring mass system stuff, the two mass and one spring. Yeah, you know that one? You already saw that, right? So there you can't just say half mv squared. You actually have to individually sum up from each body. Okay. Oh, come on. Are you serious? This is like 10th level stuff. What are they trying to tell us? It's not useful. Linear impulse. Oh yeah. So when you like, so here's the thing. You have a ball that's falling down. It will gain some velocity when it reaches over here, and then it will suddenly bounce up. Right? That's what usually happens. Why does it bounce up? You might say, okay, that's a force. There's a force that this thing puts, but then a force requires time such that it can create momentum. But we don't have time, right? It was like it just in an instant your ball went from going in this direction to now in that direction. So how did this happen, right? Do forces do that as well? Well, they do. The more real life scenario is kind of more complicated, because actually what happens is that ball squishes itself a bit, creating potential energy and all that stuff, and then the force actually gets time to like to change the momentum of this ball. It gets time to do that. But for something that's like ideal, so the ball is completely rigid, it cannot change its shape. How does this happen? How does the ball go up? Well, impulsive force. So we are assuming that the force gets enough time, and the momentum change is what we're calling as an impulse. So, usually an impulse is just the change in momentum happening at an instant. Yeah, that's the thing. Uh, So what a force usually does is that it adds momentum over time. But then what if you could have a force that adds it at an instant? It's instantly. Oh, that's weird. So here F vector dot delta t. Instead of that, your delta t becomes dt, and your F vector becomes, I don't know, it just becomes something that approaches infinity, right? Yeah. So the average force is now like infinite because delta t was very small. But still, somehow your j vector, our impulse, the change in momentum, that's still a finite value, and that's what we'll use for any kind of collisions, because we don't want to be thinking about forces really. So, right, from now on, we'll just say impulsive normal, impulsive friction, think like that. Impulsive gravity? No, not really. There's no impulsive gravity. Okay. Impulse momentum equation. Oh, come on, that's just the definition of impulse. There's nothing about an equation. Okay. Graphical significance of impulse momentum equation. So this thing, like this change in momentum, actually happens in some delta t amount, and during the delta t, some stuff happens which we'll talk about when we get to collisions. But remember, the delta t is actually not infinitesimal in real life. In ideal conditions, it might be, but in real life, you actually have this process happening where you have this getting squished, it getting unsquished, and creating its changing its potential energy to kinetic energy once again, and then it goes up. So during that time, the force does momentum change. So right during that time, there's a graph that we can draw of force versus time, and then the area between, so area under the graph will be our momentum change, right? Yeah, yeah, graph, okay. Whatever. We already know that one. Right. So now they are going to collisions little by little. Suddenly, right? Whatever. This illustration. So okay, here's the ancient exercise number 6. It has 13 questions. I guess we should stop for now. How many more exercises do they have? Yet another one. Yeah, we should stop for now. So this is it. I'll see you guys in the next video. Bye.